Homework 3, Part C, derive an expression relating flow rate and location of spherical ball in a rotometer tube. The bottom has equal diameter as the ball. There's a linear taper slope of d equals mh plus d. Little d is the diameter of the tube. Assuming that sudden expansion has no pressure recovery, viscous effects and losses due to sudden contraction in front of the ball is negligible. So the diagram for this is going to be the rotometer and a sphere. In this instance, there will be a pressure 1, a pressure 3, and a pressure 2. We know that from this statement that our pressure 2 is going to be equal to our pressure 3, but we begin with the first step that I wrote out, finding the weight of the ball and the fluid displacement and setting it equal to 0. It's going to be pi d cubed over 6 times the difference in densities from the ball and the fluid. And then we can add the weight of the fluid displacement using the pressure difference. So that'll be d squared divided by 4 times P3 minus P1, and then that equals 0. So we know Bernoulli's equation is P2 minus P1 over density plus V2 squared minus V1 squared over 2 is equal to 0. So because of what we wrote here, we can substitute 2 for 3 and solve for this. So P3 minus P1 equals V1 squared minus V2 squared over 2 times the density. Now we can substitute this into this equation. So that will end up looking like pi d cubed P minus PF over 6 is going to be equal to pi d squared over 4 times V2. We can flop it again because we moved it to the other side, times density. So from here we can cancel a couple of things. This ends up equaling 3. We can get rid of pi and pi, this, that. Alright. So the next step written, I wrote out steps for these because it's a bit longer. So bringing down what we just simplified. So we're left with, oh, and I forgot to add gravity to the first one. So the weight of the ball needs to include the acceleration due to gravity. So our dg times our density differences over 3 is equal to V2 minus V1 density all over 4. And then solving for this, we are going to move these to the other side. So 4dg times the densities over 3 density is equal to v2 squared minus v1 squared. So relating v2 to v1, we know that in our diagram, this will have a volumetric flow rate of v1a1, and that volumetric flow rate is going to be equal to the flow rate at this point, because it is one system. So relating our v2 to v1 will be v2 is equal to, we just set these equal to each other, will be v1a1 divided by a2. And we will plug this into this equation. Okay, so that'll be 4dg times our densities well, I already knew what to do, so I guess I didn't need to make that step. So it made me lose track of what I was thinking. Divided by 3 density is going to be equal to v1 a1 over a2 squared minus v1 squared. So from here, we can solve for v1 by factoring out v1 squared on each side. v1 squared is equal to, or times a1 over a2 squared minus 1. And then this one actually ends up being negligible because of the size that this will be. So we're going to remove it now. And again, this is all equal to our 4dg times our densities divided by 3 density. So if we solve for v1 here, that will look like v1 is equal to 4dg p minus p over 3 density. And we have to divide by this one, so that'll be a1 over a2 squared, and this is all under a radical. Our next step is to find a1 over a2 using this. So we know that our a1 is pi d squared over 4. And our area 2, we can get a better understanding if we draw a picture. This is d, and then this is little d. So our a2 is going to be pi d squared over 4 minus pi big D squared over 4. So now we will square this, and factor it out. That'll be mh squared plus 2mh. Move it down here. D squared is going to be equal to mh squared plus 2mhd plus d squared. So again, for this can be considered negligible, so we're going to remove that, and then we plug these remaining into here, and that will let us cancel this and this, leaving us with area 2 being equal to pi times okay, 2mhd over 4. Okay, so bringing this over here, pi 2mhd over 4, we can, this will represent a1 over a2. And then we can cancel pi's, these, this d, and then this exponent. So our a1 over a2 ends up looking like d over 2mh. Okay, so the last step to this problem is going to be plugging this into this. So v1 is equal to radical for dg difference in densities, all divided by 3 times density, and here's where we plug in our d over 2mh squared. So I'm gonna do it like this. So this will end up coming to the top. This will cancel. I guess I've been using red, so this will come to the top. These will cancel and will give us our final v1 equation as our 4 times 4 is going to be 16 over 3 is going to be equal to, or multiplied by, P minus PF. I know they're not P's, but density. Or m squared h squared, all divided by our 3 rho g. So this ends up being our final answer for homework 3 part C. I think you should be able to see that. clicker.